In the realm of condensed matter physics, the unconventional p-wave Cooper pairing in superfluid 3 has garnered significant attention due to its extraordinary properties and the breaking of parity symmetry. However, the realization of a counterpart p-wave magnetic order has remained elusive despite decades of research. This paper presents a novel approach to identifying unconventional p-wave magnetism, sidestepping the complex many-body interaction problem. By focusing on suitable non-relativistic crystal lattice and spin symmetries, the authors demonstrate the anisotropic symmetry lowering of spin-polarized energy isosurfaces in a representative p-wave magnet, CeNiAsO. The authors utilize density functional theory, DFT, calculations to confirm the symmetry principles underlying this unconventional magnetism. They observe that the parity breaking of spin-polarized energy isosurfaces is accompanied by an additional anisotropic distortion. This discovery opens new prospects in fields ranging from topological phenomena to spintronics, as it does not require strong correlations or extreme external conditions. In contrast to conventional itinerant ferromagnetism, where the SO(3) spin rotation symmetry is broken, the proposed p-wave magnetism breaks the parity symmetry, leading to a spontaneous anisotropy of the resistivity. This finding is a direct experimental signature of the unconventional p-wave magnetism. Furthermore, the identification of this novel phenomenon can be extended to various materials, including insulators, semiconductors, metals, and superconductors, under ambient conditions. The paper's approach builds upon the recent discovery of altermagnetism, which exhibits a counterpart even parity wave magnetic order similar to unconventional D-wave superconductivity. Spectroscopic signatures of altermagnetism have been observed in photoemission experiments, detecting well-resolved spin-polarized quasi-particle bands. The present work contributes to the ongoing exploration of these phenomena, providing a deeper understanding of the interplay between crystal lattice and spin symmetries in promoting unconventional magnetic orders. Unconventional p-wave magnetism in noncollinear coplanar magnets is the focus of this research. To identify material candidates, symmetry guidelines are established, emphasizing the necessity of noncollinear magnetic orderings and non-centrosymmetric crystal structures. A model Hamiltonian is presented for the p-wave magnetic lattice, showcasing the crucial role of exchange-dependent hopping in inducing p-wave spin splitting. This model is carefully designed to satisfy the symmetry criteria, including the C2 up tack T symmetry, which protects a momentum-independent spin polarization. The ultimate goal is to predict a large spontaneous anisotropy of resistivity, a distinctive signature of this unconventional magnetic phase. The authors present a study on unconventional p-wave magnetism in CeNiAsO, a material candidate that fulfills the symmetry conditions for this phenomenon. The magnetic and crystal structure of CeNiAsO is characterized by spin symmetry, C2Z, T, and a non-magnetic unit cell containing two formula units. The crystal structure consists of alternating quasi-2D layers of CEO and NIAs, with both layers taking the PBO crystal structure. The authors calculate the band structure using the Vienna A-flat initio simulation package, VASP, with the Purdue-Birk-Ernzer-Hoff, PBE, exchange correlation functionals, constrained noncollinear magnetism, and symmetrization switched off, in the non-relativistic limit. The results display a linear band crossing around the gamma point and a spin polarization in momentum space perpendicular to the direct space exchange fields. The spin space group of the magnetic crystal is identified as a direct product of the spin-only group and the non-trivial spin space group Rs times Gs, where Rs equals E, C2Z, and Gs contains symmetry elements, E, might 0.5b, C2Z, T0.5a, and others. The existence of the p-wave state with a single spin unpolarized line kx equals kz equals 0 in the kz equals 0 plane is enforced by the C2y, C2y T0.5a plus 0.5b symmetry. CeNiAsO fulfills the symmetry conditions for unconventional odd parity wave magnetic state, with broken inversion symmetry, E, P, and the existence of the C2Z, T0.5a symmetry. The full energy range band structure with the projected spin polarization is shown in supplementary materials Fig. 1. The band structure and resistive anisotropy of p-wave magnet CeNiAsO are presented in Figure 3. The DFT spin unpolarized energy bands for spin projections along the x and y axes of the spin space, and spin-polarized energy bands for the spin projections along the z-axis of the spin space, are plotted along the x gamma x path in the momentum space. The spin-splitting magnitude reaches approximately 200 MeV, marked by the double arrow. The DFT longitudinal conductivity along the x and y crystal axes is also shown, highlighting the unconventional p-wave magnetism breaking the symmetry, as evident from the plotted anisotropy of the conductivity. The proposed experimental geometry for measuring the spontaneous resistivity anisotropy is illustrated in Figure 3c. The ground state of CeNiAsO lacks the fourfold real space rotation symmetry of the non-magnetic crystal due to the anti-parallel alignment of spins on atoms along the crystal's axis and the parallel alignment along the y-axes, resulting in an additional anisotropic distortion of the spin-polarized Fermi surfaces. This is confirmed by the DFT calculations of the momentum space Fermi surfaces, shown in Figures 2bd. The Fermi surfaces calculated in the non-magnetic state respect the in-plane fourfold symmetry of the crystal lattice, whereas the spin-polarized Fermi surfaces in the magnetic state break the parity symmetry and lower the rotation symmetry of the crystal from fourfold to twofold. The momentum-independent spin polarization axis is along the spin space z-axis, consistent with the spin group symmetries. The DFT band structure is presented in Figure 3a, showing spin polarization only for the spin projection along the z-axis. The bands spin split linearly in momentum near the gamma point, concordant with the parity breaking, and the splitting reaches a 200 MeV scale. This large spin splitting in a time reversal symmetric band structure is attributed to its non-relativistic exchange origin. Figure 3b displays the DFT calculations of the longitudinal conductivity and spontaneous resistive anisotropy of CeNiAsO in the magnetic phase. The non-magnetic crystal lattice of CeNiAsO exhibits the space group P4, nmm. 129, resulting in isotropic longitudinal conductivity in the xy plane in the non-magnetic state. However, the unconventional p-wave magnetic phase spontaneously breaks this symmetry, resulting in a large resistive anisotropy. In the realm of deep learning, generative models have garnered significant attention for their ability to synthesize novel data samples that mimic real-world distributions. However, these models often struggle to maintain data fidelity, particularly when dealing with complex, high-dimensional datasets. Recent studies have demonstrated that incorporating domain knowledge into generative models can improve their performance and fidelity. This approach, known as physics-informed generative models, leverages the laws of physics and domain-specific knowledge to constrain the generative process, resulting in more realistic and accurate data samples. One such approach is the physics-informed generative adversarial network, PIGAN, which combines the strengths of generative adversarial networks, GANs, with the physical laws governing the system. By incorporating the Navier-Stokes equations into the GAN architecture, PIGAN enables the generation of realistic and physically consistent fluid flow simulations. The PIGAN framework consists of a generator network that produces fluid flow simulations, a discriminator network that evaluates the realism of these simulations, and a physics-informed loss function that penalizes the generator for violating the Navier-Stokes equations. Through an iterative process of generating and refining simulations, PIGAN learns to produce highly realistic and physically accurate fluid flow simulations. Experimental results demonstrate the efficacy of PIGAN in generating high-fidelity fluid flow simulations that accurately capture complex phenomena such as turbulence and vortex dynamics. Furthermore, PIGAN outperforms traditional GANs and other physics-informed generative models in terms of data fidelity and realism. The proposed framework has significant implications for various fields, including fluid mechanics, computer vision, and robotics, where high-fidelity simulations can enable the development of more accurate and robust models. However, limitations of the current approach include the need for extensive computational resources and the requirement for high-quality training data. Future work involves addressing these limitations and exploring the application of PIGAN to other complex, physics-driven systems. The authors numerically evaluate the integral by employing a fine momentum space mesh of 101 times 201 times 101. They define the spontaneous resistive anisotropy ratio as rho xx rho yy, rho xx plus rho yy, equals sigma yy sigma xx plus sigma yy, equals syy sxx, sxx plus syy, which is independent of the relaxation time tau.